Welcome friends to my YouTube channel. On my last lecture I have discussed about two important theorems. Okay, one is perpendicular axis theorem and another is parallel axis theorem. These theorems are necessary in order to find out the moment of inertia of different bodies. Okay, so now in this lecture I shall going to find out the moment of inertia of few simple geometrical object. Okay, so let's start. So first example that we take, that is the thin rod, that is simply one dimensional case. That is, we take the example of thin rod. Okay, now we take a thin rod. Okay, now we choose the axis passing through the one end of the rod and perpendicular to the plane of the rod. Okay, so this is about an axis passing through one end of the rod and perpendicular to the rod, obviously. So if the mass per unit length, we took L. Okay, rho, we took the mass per unit length. We take rho as mass per unit length simply. And what is the total length of the rod? That is L. L is taken as the length of the rod. Okay, so what will be the total mass of the rod? Simply the total mass of the rod is rho into L. Okay, so therefore the mass of the rod can be written as rho into L. Simple, because rho is the mass per unit length. So for L length, the total mass will be rho L. Fine. Now at first we have to find out the moment of inertia due to a small elementary strip. So we take a elementary strip at a distance x, and the width of the strip is dx. Okay, so simply we take a small strip of width dx at a distance x from the axis. So what will be the mass of the strip? So what will be the mass of the strip? That is, mass per unit length is rho, and what is the width of the strip? That is rho dx. So this is the mass of the strip. Okay, so what will be the moment of inertia due to the elementary strip of width dx? If we call it di, then mass into, that is rho dx, into the distance from the axis, that is simply x square. Okay, so this is the moment of inertia due to the small strip of width dx at a distance x. Okay, so if we integrate this expression within the limits, this is 0 and this is L, since we take the length L, so then we will find the total moment of inertia due to the entire rod about an axis passing through the one end and perpendicular. Okay, so we have to integrate this expression within the limits 0 to L. Fine. So the total moment of inertia is simply 0 to L rho x square dx. Okay, so if we integrate it, that will become rho L cube by 3. Okay, so we can write this as 1/3 rho L into L square. So this is m, that is 1/3 ml square. Since m, this is equal to rho L, mass of the rod. Okay, so this is the moment of inertia of the due to a thin rod about an axis passing through the one end and perpendicular to the length. Now if we change the axis, then the moment of inertia will also change. So how we can justify it? So now let us change the axis. How? We take this rod, this. Now we consider the axis is passing through the midpoint of the rod. Okay, suppose assume that the axis is passing through the midpoint of the rod and perpendicular to the plane. So that means if the total is L, so this is simply minus L by 2 and this is simply plus L by 2. Okay, and then the procedure will be same. We take a small strip of width dx at a distance x. So what will be the moment of inertia due to the small strip of width dx? This is simply di, this is equal to rho x square dx that we find. Now if we integrate this expression within the limits minus L by 2 to plus L by 2, because the axis has been changed, it passes through the center of gravity and perpendicular to the plane of the rod. So we have to integrate this expression within these two limits. So this will be rho x square dx. So this is rho by 3 x cube, that means L cube by 8 minus plus, this is also L cube by 8. Okay, so this is simply rho by 3 L cube by 4. Okay, so the answer will be 1 by 12 ml square. Okay, so the answer is simply 1 by 12 ml square. Okay, so you see that previously when we choose the axis through the one end of the rod, the result is different, 1/3 ml square, and now we are choosing the axis passing through the center of gravity and perpendicular to the plane of the rod, the result will be different. So it is clear that when we change the axis, the moment of inertia will also change. So this is the first simple example that I tell. So let us take another example. Okay, that is, just take the example of circular ring. Just take the example of circular ring. Okay, so just take a simple circular ring and this we choose the axis. Okay, that means about an axis passing through the center and perpendicular to the plane of the ring. Okay, we choose the axis AB in such a way that it passes through the center and also perpendicular to the plane of the ring. So we take a elementary strip, this is the circumference, and we take an elementary strip, say DL, okay, at a distance say R from the center. So we have to first find out the moment of inertia due to the elementary length DL that we consider at a distance R. Okay, so here we take rho as the mass per unit area. It is a 2D figure. So rho is mass per unit area. Okay, so what would be the mass of the elementary length DL? So mass of the elementary length dl, this is what, rho into dl. Okay, mass of the elementary length dl, that is rho dl. Rho is mass per unit, sorry, this is length because circumference is length, so I made a mistake. This is rho is mass per unit length. Okay, so what would be the mass of the elementary length dl, that is rho dl. So what is the moment of inertia due to the elementary length dl about the axis AB? So if you denote it as di, so this is simply mass of the length into the distance square, that means r square. So rho dl into r square. Okay, so what would be the moment of inertia of the entire circular ring about the axis AB? So we have to take summation, that means rho dl r square. Okay, that is rho into r square. This is what dl means, 2 pi r, that is the entire circumference can be divided into small elementary lengths of dl. So that's why summation of dl we write 2 pi r. Now what is rho? Mass per unit length. So what will be the total mass? 2 pi r rho. So the result will be m r square. Okay, so the result is mr square. So in case of a circular ring, when we choose the axis passing through the center of the ring and perpendicular to the plane of the ring, the moment of inertia will be mr square. Okay, now if we change the axis, that is, suppose we want to find out the moment of inertia about the diameter of the ring. So just you draw the ring. Okay, so this is one diameter and this is another diameter. Say this is AB and say this is CD. Now what we have learned from perpendicular axis theorem, that the sum of moment of inertia about an axis perpendicular to the plane of the lamella is equal to the sum of the moment of inertia about the axis about the plane of the lamella. Okay, so in the previous expression we have find out that the moment of inertia about an axis passing through the center of the circular ring and perpendicular to the plane of the ring is mr square. So that we choose about an axis that is perpendicular to this plane. That means moment of inertia about the diameter AB plus moment of inertia about the diameter CD is equal to mr square, because mr square is the moment of inertia about an axis which is perpendicular to both these axes. So that means what you can write? That means you can simply write, oh sorry, the marker is almost finished, so I have to buy a new one. So, and we also know that the moment of inertia about the diameter AB is, if we take I, so about CD it will also be I. So I plus I, this is m r square. So what will be by I? That is half m r square. That is, this is about the diameter. Okay, fine. So in our today's lecture we have take two simple examples, that is thin rod and circular ring. In our next class I shall going to discuss few other examples. Okay, so if you don't subscribe my channel, then kindly subscribe it to get latest videos, and the link will be given in the description box. Okay, and if you have any query, then just write it in comment section. Okay, thank you.